As a first example of applying quantum mechanics in more than one dimension, we'll look at the quantum mechanics of a point particle in a two-dimensional box. And we'll see that it's very similar to the particle in the one-dimensional box that we did earlier. To frame things, let's consider a particle of mass m, so it'll be a point mass, moving in two dimensions in the potential that in the plane, so we're only in two dimensions, x, y, and everywhere outside the box we take the potential as being infinite. And inside the box the potential energy is 0. So for x between 0 and a and y between 0 and b inside the box region, the potential vanishes. Outside, it's really a very, very high value. If there's no potential energy inside the box, the only thing that can happen is the only energy that can exist is kinetic energy. Kinetic energy is always positive, and or equal to 0, I guess, in the classical case. But so long as the energy of that is low compared to whatever the energy, the potential is outside the box, then to a good approximation we can take that to be a very, very high energy, potential energy outside, and the approximation that the potential becomes infinite outside the box is very, very good, so long as the kinetic energy is low, the particle that's inside. So even though we can't really have a high infinite potential energy, we can, to a good approximation, have systems that behave very nearly to this, at least for the low-lying states. With infinite potential, that makes the problem easier to solve, in that if there's infinite potential energy, then the particle never has enough energy to get into that region, and so the wave function vanishes everywhere outside the box. So the particle is confined to stay in this region between x equal to 0, x between 0 and a, and y between 0 and b. Well, we still have to, even though we know the wave function outside, we have to solve for the wave function inside the box for the particle, and that's just the Schrodinger equation, time-independent Schrodinger equation. There are boundary conditions, though, and we still require that the wave function everywhere be continuous, and so that means that the solution we get inside the box has to vanish everywhere on this boundary. And we'll see how that comes into play. We're now in two dimensions, though. So inside the box, it's this. The Hamiltonian is a combination of the kinetic energy operator plus the potential energy. But inside the box, as we said, that vanishes. And so we're down to essentially a free particle that's free to roam anywhere inside that boxed-in region in two dimensions. The Laplacian and Cartesian coordinates in 2D just simply becomes this. And making that identification, then we get essentially this equation for the wave function inside the 2D box. And we use the usual method, and really the only method we've had in this class anyway, of solving a partial difference equation. That's the separation of variable method. So we look for separable solutions. Psi of xy is equal to a function of x only times the function of y only. Plugging these in here, we see that the x's or the y's can come through this one, the x's can come through this one, since they don't depend on the partial derivatives, they don't have those variables. And as a result, we get this. Again, primes is a derivative with respect to the argument. In the case of capital Y prime, it's two derivatives with respect to its variable y. And these are just ordinary derivatives. Again, X double prime is the second derivative of capital X with respect to X. Getting to this form, divide through by xy. That cancels everything out over here. This side just becomes E. And then you see that the y dependence goes out here, and the x dependence goes out here. And so ultimately, you get this equation. And I see very, very often that people say, well, it's obvious then that this is a constant, and this is a constant that when you add them all up has to be this constant here. Okay? But I think it takes a little bit more logic than that, and let's do it what at least should be done initially for a few times, is we separate variables. And so what I did was I took this term over to the other side. E is a constant. These are functions of y, and so this side is a function of y only. This side over here, these depend on x, and it's a function of x only. X and y are independent variables, and the only way that can happen is the only functions of one independent variable that can be everywhere equal to a function of another independent variable y is if we have the constant function. And so I have a separation constant, which I've called E1 here, which is just this side. So set that equal to E1. Set this side equal to E1. And then I rearranged it so that they look more similar. I took this over to this side and took the E1 over to this side to rearrange the second equation in this form. And now then, to make them look parallel, I can define, really, E2. E is a constant of separation, the total energy, really, and E1 is a constant of separation. And so these two constants, I can define the difference of them to be the constant E2. And now then you have E is equal to E1 plus E2, and I can write these in sort of parallel fashion in terms of E1 and E2. The E1 and E2 are really the contribution to the kinetic energy due to the x motion, and E2 is the contribution to the kinetic energy in the y motion, due to the y motion. And the total energy is all kinetic energy because there's no potential, so it's got to be separable into those two components. And when you view it in this sense, then you see that E has to be positive. A contribution of the x component to kinetic energy is always positive, and so E1 and E2 are always positive as well. And their sum then is positive. And now it's a matter of solving this set of equations. So we move things around as usual, put the 2m h bar squared minus over to the other side. Since E1 and E2 are positive constants, then the 2m E over h bar squared terms in both of them I can define to be a positive constant. To explicitly display that, I'll write it as k1 squared and for the top one, and k2 squared is the bottom one. So I can rewrite those in this form, and then finally get the way sort of the standard form for these functions, these standard differential equations for a capital X of X and capital Y of Y. And as we know by now, there's two ways you can write those, either in terms of complex exponentials or sines and cosines. And in this particular problem, it's best to use the sine cosine form. So the general solution of the top equation is a constant integration A times sine k1x plus B cosine k1x. And the general solution of the bottom equation is a constant C of integration of k2 sine k2y and another constant cosine k2y. So there's the general solutions. And then we have to apply the boundary conditions. The boundary conditions are really this set here, all along the, in this case, the left side and the right side of that boundary region, and in this case, the the bottom and the top, and everywhere along the left side and the right side. And since these are separable, psi is x of x times y of y, but y is evaluated as 0. X of x could be anything, and so we get this condition here translates into capital Y at 0 is equal to 0. And similar analysis on this one says that capital Y of B is got to be equal to 0 for any x from 0 to a on both of these. And a similar thing happens to the left-hand side and the right-hand side of the box. The wave function has to match up with the exterior solution, which is 0, so we need a continuous wave function. And we add here along the left side x is 0, y can be anything, and so we get x of 0 equals 0. And on the right-hand side, x of a has to vanish, for both of these for any y between 0 and b. So our boundary conditions turn into these in terms of those separated x and y functions. And then we just solve these in turn. They're really one-dimensional problems. Let's do the x one first. And we have this as our general solution. A and B are arbitrary constants, which we can determine via the usual methods. At x at 0, this top one, I know that when I evaluate this at x equal to 0, then this side vanishes. Sine of k times 0, well, that's going to be 0 as well. When I evaluate this at 0, I'll get b cosine of 0, but cosine of 0 is 1, and so this leads to the equation that b has to be equal to 0. So this term falls out to satisfy this first boundary condition. The other boundary condition is x evaluated at a is equal to 0. Now I'm left with just this piece, and so I evaluate both sides of this at x equal to a. This side becomes 0 by the boundary condition, and this side becomes a sine k1 times a. And as we've seen earlier, that vanishes provided the argument, the sign vanishes for multiples of pi, and that says that k1a times n1 could be really any integer times pi. But as we've seen, we don't want the 0. If I choose n1 equal to 0, then k is 0, and I get the 0 solution, and that's not normalizable. And then we want independent solutions, and so we don't need all of those negative values of n1. So n1 goes from 1, 2, 3, etc. in integer steps, and one can solve them for k1 in terms of n1. And so we get really an infinite number of solutions at this point by applying that x condition on our x function. I've labeled it by n1 because it depends on the integer. There's an independent solution for every integer value, positive integer value of n1. Once I've got k1, I can also get the energy, because remember, k1 squared is 2m e1 over h bar squared, and one can rearrange that to this. Plug in the k1 in here. The k1 is n1 pi over a, and then simplify. And you could leave it in this form, but the one I like is this one here. H squared over 8m a squared times n1 squared. Really, I get an infinite number of energies for these integer values of n1, but I won't label this with the n1 at this stage anyway. Well, you do a similar thing for y. It's y is equal to c sine k2y plus d cosine k2y. We apply the boundary condition along the bottom. Y has to vanish. That gives us this. Along the bottom, y is 0. So 0, sine of 0 is always 0, so this term goes out. But the cosine of 0 is 1, and so that says that d has to be 0 to satisfy this boundary condition. And then along the top, that's at y equal to b. I know that y of b has to vanish as well. And that translates. Now at this stage, d is 0, and so this is our general solution that we have. And I evaluate it at b, and that has to vanish. And again, similar procedure. The sign of K2b vanishes for any integer multiple of pi. We can rule out the negative ones. They don't give me any independent solutions. And I can rule out the 0 because that gives me a non-normalizable solution. So our y functions are some arbitrary constant still times this sine of n2 pi b over y, times y. And then, of course, K2 was defined to be this. We'll really just let it be that for simplicity. And again, we can solve this one for E2, and then substitute in our K2 of N2 pi over B. And simplify, and we get this term. So at this stage, we now have the following. We found our x and y. 1 is just a sine n1 pi over ax. And then y is c, I have to multiply it together, c sine n2 pi over by. And the total energy is just E1 plus E2, and those we got from above. And now I will label these with N1 and N2. There's a double infinity of solutions. N1 and N2 are positive integers. And so I'll subscript these. There's lots of possible energies. Still need to determine A and C, and I've left those separate. You wouldn't have to, but it's always easiest to do it this way because one has to normalize the solution if I want a normalized psi. And the normalization condition in 2 dimensions is that psi squared integrated over all dx and dy from minus infinity to plus infinity has to equal 1. Now, since I've left these in the form up here, I'll go ahead and plug those into this. It's 0 outside, and so these integrals become an integral over x from 0 to a of just this term, a squared times sine squared, times c squared, the integral over y of just the y portion. And as I said, it's not absolutely mandatory that you do it this way, but it usually is easier to do these and set this, just the x integral, the x portion, equal to 1, and the y portion equal to 1, and then 1 times 1 will always give you 1. So we normalize the 2 variables independently of one another. And as we've seen, the a is just a constant, comes out. That leads to, when I set this one equal to 1, leads to this top equation. When I set this one equal to 1, it leads to the bottom equation, which satisfies the normalization. Those integrals we've done before. This one here actually turns into a over 2, and this one here turns into b over 2. But then once you solve for a, you get the capital A and capital C is the square root of 2 over a, square root of 2 over b for c. And so if you put all that together, what you have is our general solution. We've got an infinite number of solutions. Psi of n1 and 2, that's label them by these integers, is the product of the capital X function, normalized here, capital Y function, so long as X and Y are between A and B, respectively, and 0. And it's 0 outside, and then corresponding to each one of these eigenstates is the eigenvalue energy, which is given by this expression, the sum of E1 plus E2. Now, I won't write it, but once we have this, then the general solution now is a linear combination of these eigenstates. It turns out these eigenstates are orthonormal now. You can check that. I won't do it here, but they're orthonormal, just like they were in the case of the one-dimensional particle in the box. Let's take a look at it, and just to set some notation, for instance, I can get the psi 1, 1 state, so n1 equal to 1, and that looks like this. And its energy will n1 squared is 1, n2 is 1, so it's squared, so we get this expression for the energy associated with this eigenstate. We get psi 1, 2. Again, n1 is 1, n2 is 2. So 1 squared is 1, and 2 squared is 4. So we get this energy. And then you can get psi 2, 1. And here the 2 goes on this one, the 1 here. And we get a similar looking expression. And we've solved the quantum mechanical particle in a two-dimensional box. Very, very similar to the particle in a 1D box, but one gets some additional complications with boundary conditions, and the functions, of course, get extended. They have to be two-dimensional functions of x and y for these eigenstates.